do? We're gonna make it be mediated by gluons, because it's gluing everything together. Well, okay, that's one approach to physics, and then you can say, well, you know, it's there because we calculated it, but you didn't really ever experience it. You never even measured it. You just think it's there because you can't imagine how those protons could be together without it. Then they found the quarks, and they said the quarks are inside. You see, inside the protons, so they are squashed even smaller. So then they had to have an even stronger force. But they didn't want to add another force. I mean, that would look goofy, right? So they just said, well, that's the color force, and actually the strong force is just a residual force of the color force that's really strong in the middle. Well, if you make calculations for a black hole atom, and you calculate how much gravity there is at the nuclear level of a black hole that size, you have exactly the force you need to keep the atom together, to keep the nuclei together. You don't need the strong force. You're dealing with gravity in the vicinity of a singularity. You understand? And so now you can make away with that force. And so that starts to change your picture of the weak interaction and all this as well.
I would like to interrupt this presentation to give a little more details for the more technical audience. Here I'm describing the atom as a mini black hole. Many would say the atom doesn't have the mass necessary to be described as a mini black hole. However, in this presentation and in my research, I have come to conclude that the atom is interacting with a very highly structured dynamic vacuum, feeding it its energy potential and its density. And as we've seen in the presentation, the density of that vacuum is extremely large. I believe the vacuum is a highly structured, coherent energy that is feeding the atom and that is producing the dynamics that we see as particles and electron dynamics. In this view, then, the strong force becomes the gravitational force in the vicinity of a mini black hole produced by the vacuum structure. The electron is spinning at near the speed of light as a result of it being in the vicinity of the event horizon of that mini black hole. All this gives us a brand new picture of the physics of creation. Let's continue with our presentation.
What I'm bringing in is that, wait a minute, by modifying Einstein's field equation, we might be able to solve for all this and not need so much quantum theory, which is quite a change in the optics. This is one of the things that Einstein believed all of his life. That's why he was never keen on quantum theory. That's why people say that he dropped out after he wrote his field equation. He didn't really want to participate anymore. He believed that with his equation he should be able to solve all the way down to the subatomic particle, and he actually got really close, I believe, at one time, because a French mathematician contacted him that was giving him solutions to his own equation that incorporated torsion. Torsion is the distortion of an object. If you apply torque to an object, imagine you have a 2x4, and you hold the bottom and you twist the top, you're going to get a distortion of the object. Okay, that's called torsion. And so this is Élie Cartan, thought that, you know, maybe we could solve Einstein's field equation just by describing the torsion or the distortion of space-time around a gravitational field. And he solved it. The thing is he solved it, and it gives the exact same answer as Einstein's field equation. So everybody said, well, it doesn't teach us anything more, and it's more complex, so they dropped it. The only thing is that in order for something to distort, you have to have torque. in the first place. And that they never went to. They never added the torque to the space-time manifold. If you are missing 98% the mass of the universe, okay, you most likely missed the source of force that is creating what you are observing. And I believe that source to be space-time torque. Okay, the force that spins a galaxy. Imagine if you had to build a motor, how many horsepower you would need to spin one galaxy with 300 billion stars in it. A lot of force. Imagine how much force you would be missing if you didn't account for that engine. Right? That would be like analyzing the wheels of your car, okay, and all its dynamics, its mass, its angular momentum and everything, but omitting to add to your analysis the V8 engine that's spinning it. Now when you look in nature, you can see these dynamics. Look at this. This is a galaxy. Okay? And galaxies have galactic halos. Can everybody see this? It's like a very fade, big sphere around the galaxy. And when, when we look at galaxy, typically we only think of the galactic disk, right? And that's because in the galactic disk there's the most amount of density because the sphere around a galaxy has a huge surface, so things spread apart, so it's not as easy to see. But there's actually more stars in the galactic halo around galaxies than in the galactic disks. And then here you can definitely see a huge vortex going into the black hole at the center of the galaxy. We can't see the one below it because, these are very far away and we don't have that great of optics and so on. But we know that in general, there is always, or typically, two huge vortexes going into center of black holes. In the case of our galaxy, that vortex is, I believe, 3 on the north pole of our galaxy, if you're looking from our perspective, is 3,000 light years long. 3,000 light years long. This is, at the speed of light, it would take still 3,000 years to get to the end of the vortex. And it's filled with gases and high velocity dynamics and high energy dynamics enough that it's actually visible thousands and thousands of light years away from it. Imagine how much torque you need to produce that. Isn't that an obvious example of water going down the drain? Okay, now you'd say, well, wait a minute, when we see these vortices and we follow the particles, they're spitting out. Okay? Well, okay, if water is going down your drain, air has to move out of the drain for water to come down. That's the exchange. We only see the outside of the event horizon. We only see the radiating part of the event horizon. We don't see the space-time torque going into it to force the system to have angular momentum. And so the result is that we live inside a black hole. That's why it's black out there at night. Okay? And what we see inside that black hole are smaller black holes, smaller scale black holes, that we're on the outside of. So what do they look like? Radiating stars. Radiating objects. Because we're on the outside, we're seeing the plasma Coriolis forces dynamics on the outside of the thing. We see the radiative side, we don't know about the contractive side, and that's why most of our physics is based on the radiation. But there's an exchange between the two, and this is the exchange I'm showing here, and that we calculated.